Welcome back, and I hope you and your family are well. So what we're going to look at in this lesson, and perhaps a series of lessons, is the topic of sound. Now, it's quite a big topic, but it's one I particularly enjoy. Now, I think you probably know more about sound than you think you do. So I'm just going to whiz through a few of the ideas that we're going to cover, and then we'll do some experiments and explain each one in turn. So you need to know something about sound being a vibration. You need to know that sound is a vibration of a material. So you can imagine an earthquake being a vibration in the ground of the earth, and you can imagine me talking to you now as being a vibration of the air, though you can't actually see it. If there's nothing to vibrate and we've got a vacuum, you won't hear anything, sound won't travel. We'll talk about the fact that sound has a speed. It's actually about 1 million times slower than light. So you all know that when you see someone hit a cricket ball, you see them hit it, and then click, you hear the sound later. Or looking up at aeroplanes in the sky, as I'm always doing as a keen private pilot. And you know to not just look straight up where you hear them, because they will have moved on since then. Thunder and lightning's another example. So you know that about sound. We need to look at how we hear sound and what low notes we can hear and what high notes we can hear, and what happens if we go above the high notes and we go below the low notes, the ones we can't hear. What's going on there? We also need to look at the shape of the sound wave, in other words, how the air actually vibrates. And we need to be a bit more mathematical as well, and actually draw some of these waves and take off them key features: how loud they are, the amplitude, how rapidly they go up and down, the frequency, and the shape of the wave from peak to peak, what we're going to call the wavelength. Now, a lot of waves that you'll imagine, like I did with my hand then, will be this sort of shape, and a sound wave isn't actually that sort of shape. It's a bit more complicated. But when we draw them, it's so much easier to draw shapes that look like the waves that you'd recognise on a beach. So the plan is, for the next bit of this video and maybe 2 or 3 more, to cover all those topics, and by the end of those you should have a really good understanding of what sound is and how it works. So there's an experiment you can do at home, but you've probably done it so many times, and it's the one that annoys your teachers. You take a ruler, doesn't matter what it's made out of, rigidly hold it down on the end of a table and give it a twang. Okay, and you'll notice it vibrates. It goes up and down and up and down. And you'll notice something else as well. If you make it longer, it vibrates less rapidly per second. And if you make it shorter, it goes up and down much more rapidly per second. Now, there's a number of things going on here. Firstly, you can hear it vibrating, so there must be a way of the sound energy getting from the tip of the oscillating, vibrating ruler to our ears. And that's the sound being carried through the air with a wave. Secondly, if you make the ruler short, you get a kind of high note, a very, very rapidly vibrating one. A high frequency sound wave, in other words, one that we perceive as a high note. And if you make it long, it flops up and down at a much lower rate, a lower frequency, and you get a low note. And I always remember pupils doing this, taking the ruler and shortening it or making it longer. Doesn't work very well with this one, but should hear the note go up. As the vibration gets more times per second, the frequency goes up, and so we get a higher note. Now, the way the musicians will do this before they play is they'll use a tuning fork. And a tuning fork can be looked at in a couple of ways. It's got 2 prongs that, if you flick them, vibrate. Normally you bash them on something like that. And it's easier to put it on a surface that's going to vibrate as well, that amplifies the sound, that makes it louder. And this indeed also is something that's vibrating. It's a vibrating object just like the ruler. There's a little trick with tuning forks that a lot of people don't notice. If you hold it up like that and rotate it, okay, can you imagine it's sort of making the shape of a cylinder? It's making the shape of a wine glass. And I bet you all have licked your finger and gone ee around a wine glass, and that vibrates in a similar sort of way to a tuning fork. So this is a sort of medium length tuning fork. I'm just going to reach forward for a shorter one. Okay, so everything that I've taught you so far, what do you think the difference is going to be between these two? So this is a longer one, plays that note, and this is a shorter one, plays a higher note. I don't know if you can hear that, but this produces more rapid vibrations, more vibrations per second, a higher frequency, and therefore we hear a higher frequency as a higher note. Okay, here goes for our next experiment. So what I'm going to use here is a loudspeaker. Just remove Bjork for a second. Okay, you usually see loudspeakers at concerts and things in big boxes, and they're normally like that. Okay, they're facing towards you and they're vibrating in and out. You can sometimes see them vibrating. Well, then they're going to make sound, aren't they? A sound wave. Put two of these on a headband. Looks a bit ridiculous, one on this side and one on that side, and you've got a pair of headphones. Make them really tiny and poke them into your ears, and you've got the little earbuds that most of you have these days. Okay, so I'm going to point the speaker up at my roof purely because it sits on the desk better that way. On you go, Bjork. Okay, and what I've got here is a thing that produces electronic vibrations. It's a signal generator, and you might be able to see the screen. You've got to be a bit careful. There's a decimal point on here, so it's reading 0.9 at the moment. And I'm going to turn it on, and you'll notice a very, very low frequency vibration. Okay, I can't hear it, and neither can you, because this is below the sound that humans can hear. This is infrasound. I think whales and things, I think, can hear sounds like this. And if they can, it means they've got a range of hearing that can go into the lower frequencies. And it also means that sound must be able to travel through water if they can hear it. Okay, so let's turn up the frequency. And you might see what's happening on this frequency measuring device here. Okay, so it's reading, let's just get it, about 3 vibrations a second. Okay, so here's one to learn. 3 vibrations a second is named after a radio engineer who did a lot of work on vibrations, Mr. Hertz, Heinrich Hertz. So 3 vibrations per second, we're now going to call 3 Hertz. Okay, so let's go up in frequency. Okay, and I'll just lean across and look at what it's reading now. And that's 10 Hertz. And you get a really interesting effect at 10 Hertz with a teddy bear, this teddy bear, something that's beyond the course we're doing. You get something called resonance. In other words, he goes up and down, but his arm seems to sort of vibrate on its own. It likes to vibrate at 10 Hertz, at a frequency of 10 Hertz, so it shakes really well. That's the sort of physics about how all musical instruments work. Okay, it's probably going to fall over, but let's go up in frequency. And we're as high as we can go on that setting. So I'm going to go back down to the low frequency. There we go. Multiply by 10. Have a look at the scale again. Okay, a higher frequency and a higher one. It's going to give Bjork a bit of a headache. And I hope you can begin to hear that now. Okay. After a while, the loudspeaker goes up and down so frequently. The frequency is 32 Hertz at the moment. That you actually can't see him moving. He is moving. So we'll get rid of him. And I'll put a ping pong ball on. And there you go. Oh, it does sometimes jump off. There's the proof. Almost. There we go. Okay, there's the proof that the loudspeaker is vibrating. And it's vibrating at a frequency of 32.6, I think it is, 32.6 Hertz. So it's going up and down, 32.6 times per second. Okay, so let's take our understanding just a little bit further. So you understand about frequency, how many vibrations per second, and that's measured in hertz. You might notice the machine now is reading 1, which doesn't make sense because this is a very high frequency note, and I hope you can hear it. But I've set it to the 1000 hertz scale. So you now know that 1000 vibrations a second we're going to call 1000 hertz, and we're going to abbreviate it to 1 kilohertz. This sound is one you might recognise quite a bit. It's used for test tones when a satellite TV channel is off, and they might just have a coloured card on the screen, and they'll play this tone so the engineers can test the transmission. But I can do something with this. I'm just going to turn that down. I hope you can't hear it now. I hope you can hear it now, and now, and now. It's getting louder. It's a bit annoying for me, so I'll turn it down again. Okay. Now, I didn't change the note then. Haven't changed the note at all. Haven't changed the frequency. What I've changed is the amplitude. Okay. Think about an amplifier. Amplifier means make bigger. So if they were water waves, waves coming on a beach on a calm day are not very high up. They have quite a low amplitude. And on a really windy and stormy day, they're very, very tall. So they have a high amplitude. So what's happening is the loudspeaker is vibrating up and down 1000 times a second, 1 kilohertz, through a small distance. And it's now oscillating up and down, you can't see it, through a bigger distance. So there's your next learning thing about sound and waves. Amplitude is how much energy, how loud, and how much the thing that's vibrating goes up and down, whether it's a low amplitude wave or a high amplitude wave. So the note, the frequency stays the same, but we can change the amplitude and keep the note the same. We can change the amount of energy, the amount of pressure in the air, and the amount our eardrums are pushed by changing the amplitude. So here goes for one of my favourite sound experiments of all. What we're going to look at now is the range of human hearing. And what I mean by that is what's the lowest frequency we can hear and what's the highest frequency we can hear. Now, it's not going to work very well on the camera, I'm afraid, because my camera doesn't record all notes equally well. But let's give it a go anyway. So what I would do in my classroom is I'd get you all to put your hands up. That includes me. And I would say, right, guys, put your hand down when you can't hear the sound. You have to be completely quiet. Okay. And I've actually found out that some pupils are suffering from a bit of deafness when we've done this experiment. So I'd have my hand up at the moment because teacher said put your hand up. But in fact, I'd put it straight down again because I can't hear that. Can't hear that at all. It is vibrating. Okay. And I've set it for 10 hertz. So what I'm going to do is turn the amplitude down. Okay. Scroll this back down again. And turn up the amplitude. And what have we got here? We've got 10 hertz. And I'll just keep turning this up until I can begin to hear it. Oh, I've got that. Take the ball off for a second. Again, I don't know on the camera if you can hear that. I can just hear that, and you would if you're in my classroom. So your hand would be up. And that's 20 vibrations a second, 20 hertz. So let's go up in frequency, number of vibrations per second. Okay, all good. I'll just look at my screen. 112 or thereabouts hertz, so 0.112 kilohertz, and we can hear that perfectly well. So I'm going to turn down the amplitude. Okay, scroll this back, and I'm going to allow myself to produce sounds of a 10 times higher frequency. So there we go. So let's go up. Now I'd have to have my hand up at the moment. So I hope you can hear that on the camera system. 1,123. So turn it down a bit. Okay, 1.123 kilohertz. So I'll do the same thing again. Bear with me. Turn the amplitude down. I need to scroll the frequency down. Okay, and here's where the interesting thing happens. Turn the amplitude up. I hope you can hear that one. Go up, 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 up. Turn the amplitude up a bit, up, up. Just got my hand up. Gosh, I can still hear it. Okay, so that's 11 kilohertz, 11,000 vibrations a second. Now, you might have lost that from the camera, but I promise you this is working and I can hear it. So I have to turn the amplitude down, scroll back down again. Okay, I so wish I could do this with you in class. Okay, 10,000 vibrations a second from the loudspeaker. It's actually pretty loud in here. Again, I've no idea if my camera will pick this up. Okay, let's hand up, FJ. Right, now what's really interesting is I can't hear that. Okay, I can't hear that. 13 kilohertz, 13,000 sound waves per second. Why is that? Okay, so if you don't know my background, I was a DJ when I was much younger and I was listening to loud sounds all the time. In fact, one of the reasons I gave up is I didn't really like the volume that I had to play. And I used to wear ear protectors when I was actually doing it. I learnt the drums when I was a kid, which was very percussive and very loud. And since my sort of mid-20s, I've been flying quite noisy aircraft. So I've damaged my hearing, okay? Which means that you really, really shouldn't listen to loud sounds for extended periods of time. Okay. Now, if we were in class at the moment, you guys would be going mad. You'd be going, oh, please switch it off. Okay. And I'd go, nope, I can play this for as long as I like. Okay. It's actually really annoying for younger people. You've got better hearing. Okay. Because you're younger. So protect your ears, please. Don't listen to loud music for long periods of time. So you guys would still have your hands up. I wouldn't. Let's turn the frequency up. Okay, and most of my students put their hand down at about 20,000 hertz, at about 20 kilohertz. Some can go a bit higher, some drop off a little bit earlier, okay? But what that means is above 20,000 hertz, let's go to 34,000 hertz, 34 kilohertz, we can't hear at all. So let's just quickly summarize. And I don't even need to turn the amplitude down because that's playing a loud note, but I can't hear it, and I bet the camera can't. So humans can hear from 20 vibrations a second up to 20 kilohertz, 20,000 vibrations a second. That's an average human, 20 hertz to 20 kilohertz. Okay, below 20 hertz, we're in the realms of infrasound, below sound, and that's usually large mammals like whales and things. And above 20,000 vibrations a second, 20 kilohertz, that's ultrasound. And ultrasound is what bats use. Okay, bats use ultrasound. They go beep, and it hits a wall, and it comes back, and they work out how long that took, so they know how close the wall is. They're using an echo. They're sending sound out, and it comes back. And if it comes back quickly, they're close to the cave wall. And if it comes back after a long period of time, they're further away from the cave wall. So they're pretty clever mathematicians, and they're using echolocation. We can use ultrasound for firing up to my roof and back. And if we time it, we can work out how high the roof is. That's kind of an electronic ultrasound tape measure. And we can send it into mum through her tummy. It hits the baby, which is a different type of material, echoes back, reflects back, and then you can turn that how long it took information into a coloured picture on a screen, and you can see the baby developing inside a pregnant woman. Okay, and because it's using sound, it's perfectly safe. We're not using X-rays, which would be very dangerous. So we'll draw things to a close on this part of the sound film. Maybe just wind back a bit and have a think about what you've learned. So you've learned about what sound is, how fast it goes. We've just talked about its uses and echoes. We've talked about frequency and what it's measured in. we've talked about amplitude and what that means, and we've done the range of human hearing, below it infrasound, and above it ultrasound. So you've got a pretty good understanding of how sound works now. So I'll end this film and I'll make another one with a little bit more information about how sound waves work very soon.